Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Digital Twins for Structural Engineers. My name is Amanda and I will be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders, past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Bentley Systems. Bentley Systems is the leading global provider of software solutions to engineers, architects, geospatial professionals, constructors, and owner-operators for the design, construction, and operations of infrastructure. Bentley's microstation-based engineering and BIM applications and its digital twin cloud services advance the project delivery project-wise and the asset performance asset-wise of transportation and other public works, utilities, industrial and resources plants, and commercial and institutional facilities. Today, we will hear from two speakers, followed by our live audience Q&A session. And I encourage you to send questions through to our speakers via the YouTube chat box during today's presentations. Without further ado, I'd like to welcome our first speaker for today, Cesar Caiduro. Cesar is a digital engineering specialist and an experienced DE manager. An early adopter of different related technologies, Cesar has over 15 years' experience using multiple software packages and has a strong background and interest in researching, developing and implementing strategies, methodologies and workflows. His key competencies include digital engineering standards, development, implementation and enforcement, execution plan development, and the implementation of automated workflows to support BIM standards and productivity. Cesar's background covers options development, construction delivery, and shop drawings documents, and experience in civil structural mechanical, electrical, and plumbing. He also brings skills in developing automation to fulfill delivery requirements and strong knowledge in different programming languages and computational design. Please join me in welcoming Cesar Caiduro. Thank you.
Thank you for the great introduction. So let's just start and jump into it. Again, I'm Cesare. I come with more than 15 experience in digital engineering around the world. So for me, really, it's all about simplicity. And I usually say that simplicity is the most sophisticated method. And I'll come back to this at the end of the presentation. So what is digital twin all about? You know, it's all over the places. And to me, to be honest, right now is literally a buzzword, and I like this this picture. You can find multiple and different ways of demonstrating with the graphics the digital twin. Someone is placing a building, someone else is placing a face like this one because wants to mention a little bit more about machine learning and artificial intelligence behind digital twins. But it's literally it's the way you wanna manage your asset. You can manage it from a different perspective. So what is all about? Well, for me, digital twin is made by three major components, and again, everyone can come with different ideas. But for me, it's all about having geometry, having data attached to this geometry, and having a place where you would like to store this information to be able for stakeholders to engage with them and possibly identify, and streamline those informations. So let's dig a little bit, dive into these three components. So collaboration. I will start from the very top one, so the outside cloud in the picture. So every single major vendor is coming with a different portfolio and different solutions for collaboration around digital twin. Autodesk is coming with that. Bentley is also coming with digital twin. And iTwin, and also if you start thinking about artificial intelligence behind digital twins, we see companies like iPar in the States or Archistar AI in Australia that are looking really to streamline again information. It's all about harvesting this information, manage this information, attach this information to a piece of geometry with different level of details. It doesn't really matter the level of details at this point in time, but and then being able to produce a representation of both geometry and information. And everyone is coming to a different place during the life cycle of the projects. Some of them are in the concept stage, some of them are more in the construction stage. But at the end of the day, it's really made by three components: geometry, data, and representation of the data. For me, these all look very scary because you can really tackle the problem from different perspectives. So I would say there's not the perfect solution to represent these information and collect these information. It's very project related or very client specific, the way you want to manage design information and present design information as an end goal. So I will probably concentrate a little bit more on the geometry side of things and on the data side of things. So let's start with the geometry. Again, for me, this is probably the biggest piece of the cake. You can't have a real digital twin if you don't have a geometry. And if you don't have data and you have only geometry, that's not a digital twin, because data is all about. So let's concentrate a little bit on geometry. And I would like to take the opportunity to talk about computational design and how we can use computational design to speed up the process of creating geometry towards the idea of having a digital twin. And we'll focus about specifically around structures. So I'm very civil infrastructure biased. So the two examples I'm going to talk about are around retaining structures and tunnels. Both of them coming from well-known projects around Australia. I can't really mention one of the two projects, but it's not relevant to this presentation. So for those of you that are not really familiar with computational design, what is computational design? This is really another buzzword like digital twin these days. So for me, computational design, it's like back in the days with a calculator. So you have numbers on one side, and then you type those numbers, and then you have an equation on your calculator, and then you get numbers on the other side. Well, computational design or parametric design, depending on how you want to express the constraints between geometries, it's literally the same things. So you have numbers or geometries on one side, then you have a black box with rules and constraints and mathematical equation, but at the end of the day, you get on the other side some other piece of geometry or some other piece of numbers. So it's literally having inputs, having some kind of manipulation of those inputs, and then on the other side you get other outputs that can be inputs for another piece of the workflow, or can just be the end result. If you think about, for example, like a structural analysis result. So there's different platforms and different ways to approach computational design. There's definitely an easier way, what we would say, which is around using visual programming. So again, visual programming today is very popular. It's becoming much more popular within the engineering firms. But it's really being able to use building blocks graphically to build complex workflows. So if you think about, again, an equation, you can have your variables, then you can have all your rules, addition, multiplications, and whatever is going to be the rule. And then on the other side, you have the equal output. But instead of writing that with a very complicated formula, then you can use like building blocks and then connect those with connections. So this is a typical example of a visual programming workflow, which is definitely much more easy and easier to understand, read, and extend compared to I would say, the traditional code. You can still have traditional code within a visual programming, but it's definitely less compared to a fully fledged, I would plugin, traditional plugin. So there's an easier way. There's less the learning curve is less steep compared to a programming code, and it's much more visual. So it's easier to understand even when you come back after a few months on the same workflow. Goodbye. So let's talk about now, if we move towards the next slide. For me, really, using computational design and visual programming, it's literally like sketching on a piece of paper. And I love this slide because this is really representing the full idea. So visual programming is really sketching with a pencil. And once you are happy with the sketch, then you can move into a more production environment and then build a plugin using programming language like C# or Python or whatever it's going to be. But the difference is when you are within the visual programming environment, making changes to your workflow is much easier than making changes when you have a fully fledged coded environment. So that's the full idea of using this slide, basically. So, but what I would usually like to say is that, when you have great powers, that comes with great responsibility. And by the way, that's not from Spider-Man. It's from a French writer called Voltaire. Then Spider-Man just borrowed it. And again, there's everything looks impossible until someone does it, and that comes from Batman. And as you can imagine, I'm a huge fan of comics. So computational design is very powerful, but comes, with complexity. So you can use computational design, to solve very complex problems in engineering. Like, for example, parametric geometry modeling, we talk about it, form finding, automating design processes. If you think about panelization in very large and complicated facades, a high-rise optimizations when it comes to building, and of course, structural facade engineering. So those are all very complex problems that can be solved with computational design. And the idea is that you don't only can solve that problem, but you can solve it quickly, and you can run multiple iterations of the same problem and come up with different solutions. And at the end of the day, choose which one is the right solutions for your specific engineering requirement. So going back to the process is very simple. You start with some design idea and criteria. Then you go into the engineering piece of this design criteria. Then you move into more detailed modeling. And at the end of the day, we all want to see drawing coming out from these models. And at the end of the day, we want to see drawings and models driven by data within the process. So for me, this is really another interesting picture that defines the transition from what was the world before computational design and smart objects, and the world that we are moving towards now with digital twins and smart objects. So the picture here at the bottom right is an Excel spreadsheet. So who doesn't love Excel? We've been running projects for years, and we're still running projects and structural analysis literally based on Excel. And Excel is an example of digital twin. because contains information about geometries, contains information about assets, contains information about location, contains all types of information. And at the end of the day, you can present those information in a very simple way, in a very simple form of a database, because Excel is a database at the end. So it's not relational, it's not a complex database, but it is a database. So what we're moving towards too, it's more the object on the left side of this slide, which is a smart object. And the smart object includes all the relationships that we have built into Excel, thousands of Excel spreadsheets in probably just one single object. So the object is clever enough to understand how to stretch and how to flex depending on engineering criteria. And then using computational design, then we can put together more smart objects, and then they can all be combined into complex structures, and then provide the right information for different stakeholders, being structural engineers or being project managers or being construction managers, depending on who is looking at the model in a different from different perspective. So those are some of examples, some of the screenshots of computational design modeled objects. So that barrier, precast barrier that you saw in the previous slide was part of a bigger picture, a bigger model that includes maybe hundreds of precast barriers. But as you can appreciate from this slide, they all come with very different geometries, they all come with different constraints, they all come with different locations, which is what at the end of the day is the geometry within a digital twin. So the geometry piece of it is basically the representation of that geometry and all the data attached to that geometry, which again will feed different stakeholders depending on what is the use case that you really want to get from a digital twin. Those are, again, other examples of retaining structures, all driven by computational design. And at the end of the day, the engineer wants to take some of these informations into a developed elevation that might be just good enough for a structural engineer to make some adjustments to the structure, or having some kind of idea on the structure itself. Again, other example. This is a retain wall made out of panels. It's in RSW type of wall. Again, same idea. The beauty of it is that now we can get a developed elevation, pretty quickly from a model as soon as we have a new design change in the model, which wasn't really possible with traditional methods. And also at the same time, that model is going to be georeferenced, and we can use it for collaboration, coordination, and eventually finding interfaces with existing structures. Again, this one is another example of a complicated RSW, which transition into an L-shaped wall and then finish with a barrier footing wall. So you can see that you can have a very huge complexity in terms of shapes and in terms of information attached to it. So each one of these single panel can be tagged. Each one of these single panel can be quantified. Each and single precast barrier can be quantified and tagged, and also all the railings on top of the barrier can be quantified, can be manufactured and then shipped to the construction site with the right information and then just installed. So each and single barriers come with anchors, bolts information, which again is part of the big piece of data coming together with the digital twin. And finally, drawing production. Drawing production has been always completely separated from the model. But what we're trying to achieve today is that drawing production is yet connected with the model. So whenever we change the model, we get a new drawing out, and we don't have to think about using drafting times to go and change text and change information just manually, because 80% of this information, I wouldn't say 100%, but 80% of this information are coming straight back from the model as a tag, which is the clever and smart way of demonstrating text. So if we change the size of the footing, the associated dimension on a drawing will change according to it. So will change the volume of concrete, for example, that is in another spreadsheet or in another dashboard for the project managers or for the procurement manager. So everything is well connected, and the model is literally the single source of truth where we attach all this information to. So let me give you another example of computational design, this time for tunnels. And again, the process is very simple. You start from the design of, this is a TBM tunnel, and it's a rail tunnel. So you start from the design of the center line of the alignments, and then you come up with the digital representation of the tunnel, which then can lead to different use cases. Again, we use extensively parametric design here just to be able to iterate to the process of creating multiple options of the same model and then being able to extract information from this model for the different stakeholders. This specific model was the platform of the station made out of caverns. And the main goal of this model was to have a verification of the tunnel ventilation system requirements, which wasn't really possible just with 2D drawing. So we extracted a portion of this model and a different level of detail of this model to be provided to the tunnel ventilation engineers to run their calculation and CFD simulations. But the same model was used by the construction team for staging of the construction and understand exactly the breakthrough of the TBM through the and simulate basically the TBM passing through the station. So this is an abstract of the TBM tunnel, and the TBM is complicated by itself. So the way the rings are placed, the way the rings are modeled, and the information associated with each of the ring is probably worth a separate webinar by itself. So we use this to what I would say mimic the idea of the TBM. So using again computational design and very high detailed model, we have identified the ideal trajectory of the TBM. And for different reasons. One of the reasons being finding interfaces with the existing foundation of existing buildings. Another was, for example, to identify the possible location of cross passages and literally try to minimize as much as possible what would be the ideal solution of basically the path of the TBM. We all know that the TBM will be corrected and adjusted throughout the process of excavation, but at least this will give us, for example, an estimate of using in conjunction with a geotechnical digital twin model. This will definitely give us an evaluation of the different materials we are going to excavate, and eventually we will understand what will be the timing of excavation of that specific portion of the tunnel. Again, attached to other processes like generative design, you can come up with an ideal solution to readjust the trajectory of the TBM to, for example, maximize the amount of excavation in rock, or to minimize the timing of excavation and sort of cost estimations types of rules. So the colors here are not just fancy colors. The colors here will give you an idea of how the different rotations of the rings and the positions of the rings based on the of the possible rotation metrics of these segments. But the main idea is that, again, you want to minimize the deviations of each of these rings from the design center line of the tunnel. So this is a very quick video. I'll probably go fast on this one, but the main idea is again presenting you with what it looks like to be a very complicated solution through visual programming. This is all a spaghetti connection, but at the end of the day, you really want to change few inputs, which usually are on the left side of the workflow, and then you have loads of magics happening in between, which eventually are just mathematical rules or geometrical rules. And then on the right side of the flow goes always from left to right. On the right side of the flow, you'll find all your outputs. Again, those can be just simple numbers if it is a report, or can be other geometries. In this specific case is the tunnel itself, is the model of the tunnel. But then it comes with all the information attached to it. Again, cross passages, it's another huge problem. You kind of need those cross passages, especially if you have a twin tunnel connection, and you need to place cross passages at specific distances between them. But you also want to place them and excavate them and cut the existing rings in a specific location where it's best to place the cross passage. So again, using computational design driven by rules, we could identify the best position for cross passages, identifying a cut of 5 rings as an average, and then try to identify which of those rings would be best fit for the cut in terms of locations and types. So again, it's all coming with rules that all the engineers have in their minds, but it's just translate those rules into algorithms that the computer can understand and can manipulate. Another use case was the kinematic envelope, again demonstrating that the rolling stock fits within the tunnel. There's no interfaces with MAP, and most importantly, also understand and design the walkway based on the location of the kinematic envelope. Again, all driven by rules, all driven by geometries, all driven by data, because at the end of the day, we exported a report of the walkway set out. So let's briefly go into data. Again, this is the biggest piece of the digital twin, I would say. So we can't have a digital twin if we don't have some kind of geometry, but we could have a digital twin with no geometry, but we definitely can't have a digital twin if there's no data attached to it. So what I would say, briefly touching on the data, we're looking for some specific areas when we think about data in the digital twin environment. So we definitely want to have something where we can store those data, and can be a proprietary platform, but it can be also an open source data repository. We definitely want to think about understanding the version of the data. We want to be able to collaborate on those data based on the different stakeholders having different reports. We want to have interoperability on this data. So again, not only different stakeholders in terms of personas, but also different stakeholders in terms of companies, especially when you work in large joint ventures setup. And then, of course, we want to be able to have this data as structured as possible to be able to then run some kind of business intelligence on top of this data, being, again, reports for the constructions or reports about progress or any other type of reports. Maybe we want to use sensor data, so we want to collect sensor data attached to our digital twin. If we look about the personas I was talking about, we definitely can see the computational designer playing an important role in creating that geometry at the real beginning of the process, and then taking the initial model and moving those models into more a design and drawing production environments. So this will contribute to the computational design workflow, and then starting to attach information. So the information manager comes into place, and of course engineers. So those are the major stakeholders for us. Structural analysis, you name it, reports, again, construction sequence, anything that can be driven by data that are stored in the model. Definitely the engineers are interested into, and those are the major stakeholders for us. But then you still have external designers, for example, peer reviewers that want to access the same information. So again, different stakeholders, different access model, different data you want to expose, but at the end of the day, you still have your single source of truth. And of course, the end goal is to produce a digital twin that the asset owner can take, can progress in starting new processes like facility management or maintenance management on top of the asset. So it's all important that we do have a centralized approach to it, but definitely everyone needs a different piece of the cake, depending on the life cycle of the project, depending on where you are sitting between the stakeholders. But everyone has a different approach and different needs to contribute in a different way to the digital twin. So for us, this is really the holy grail of computational design and digital twin. So what you want to see is literally having your model from an architectural perspective, having your engineering model, having your computational design workflows to drive those models, and then extract structural analysis from this model. But then on the other side, you want to be able to provide access from different devices, maybe using web application, but you want to also present information using dashboardings, maybe Power BI. And then at the same time, you want to run optimizations, algorithms on all of these information. And don't take me wrong, optimization is not only on the geometry side, but can be also on a data side, because maybe, as I mentioned, you have data about excavation. You want to minimize the excavation time. So you want to run some kind of optimization algorithm on the excavation timing, which will then drive the geometry. So from my experience and my lesson learned, computational and generative design are really here already to reduce what I like to call the time to market. So every time there is a design change, we need to produce new information, we need to produce new geometry, we need to publish those information and geometry. So computational design that can definitely speed up this process. I would say that designers and engineers having these digital twins in their hands can take more informed decisions. So for me, really the model is not anymore the end product, but is the input product for all of these design processes. Sometimes it's not cost effective, and I can get that. So the first project definitely need to do more investment in terms of setting up these environments and workflow, training the people, training the users, and provide that awareness that this is the right way to do it. And then, of course, as I mentioned, documenting properly the processes and training and upskill the users to be able to take into account these new ways of designing. It's really important. I like to call it always keep it simple. Just to mention something I mentioned at the beginning of my presentation, just always a good balance. I saw multiple times creating very complex algorithm, very complex coding, very complicated workflows, but very difficult to change, very bespoke for project. So try always to break it down into simple steps. Try always to make the algorithm to look simple and build your building blocks to then build complex algorithm at the end. So this will make a lot easier to change along the way. And again, computational design can be your sketching tool before you go into a more formalized approach. So with that said, I'm done and I'm open to take any question.
Thank you, Cesar, for your insights. I'd now like to welcome our second speaker, Josh Taylor. Josh leads product management for Bentley's structural analysis and pipe stress software groups. He has a special interest in the applications of interoperability to structural engineering and using these ideas to improve productivity in design and construction. During his 17 years at Bentley, Josh has helped organisations of all sizes understand and adopt new technologies in their process. He received degrees in civil engineering from Purdue University and the Georgia Institute of Technology. Josh is a registered professional engineer in the US and the states of California and Washington. Please welcome Josh Taylor.
Okay, thank you, Amanda, and thank you, Cesar, for a lot of great insights in your segment. It's great to be speaking here today with all of you. Again, my name is Josh Taylor. For a little background, I lead the product management function for Bentley's structural analysis and design software. I work very closely with the teams that build applications like MicroStrand, RAM Concept, LimCon, and STAD, which are all structural analysis and design software applications. My job really is to make sure that we're building the right technology for the structural engineering community. I'm a structural engineer by practice and spent some years working in the building design consultancy before joining Bentley. One of the things I really enjoy about sessions like this is that we get to hear the industry perspective. Really, the way I'd like to think of my piece here is not so much as a presentation, but more as a conversation. And as we go, I encourage you to give your own insights on what I present using the chat window, and we can use that as a springboard to further conversations on this topic. I'm going to talk today about the digital twin in the context of structural engineering. And much of what I'm going to talk about is really just a product of what we're hearing from you, the practitioners, in how you want to work. And we're shaping the technology accordingly to your needs. And what I'd like to do is spend some time just sharing some of the ways that we're shaping our technology and how it can be applied to the problems that you face. So the digital twin is a concept that some of my fellow colleagues at Bentley have talked about in previous editions of this webinar. Dave Bodie talked about the application to the transportation sector, and Scott DeVoe spoke about the use of digital twins in subsurface soil conditions and investigations. Here are a couple of other examples, each of which is from Bentley's Year in Infrastructure Yearbook. The first is the Warragamba water pipeline in Sydney, where drone images were used to create a 3D reality mesh of the pipeline, essentially helping to automate the inspection process. The second is more of a hybrid of a reality capture and design model that was applied by Taylor's to Goulburn Valley Water in Victoria. Taylor's used the reality captures generated with the context capture product to add the reality meshes to a custom web application that they created. And one idea I think we can take from all of this is how a digital twin is applied to and used by a given construction trade or engineering discipline is still pretty wide open and evolving quickly. So this is a commonly used view of how the design and construction profession has transformed digitally over the years. We started with CAD, then we progressed to BIM, and now we're in the midst of digital twins really becoming the digital centerpiece for construction projects. And there's something I would suggest is a little different about the digital twin than BIM or CAD. And that is that when we unpack what's important about it to each construction trade or engineering discipline, we're probably going to find that there are some differences in what's important to each of us. The information that's most useful to each trade will vary possibly. And the journey we're on really is to determine what is the most important data in making structural engineering decisions that impact design, construction, operations, and future renovations or expansions of infrastructure assets. I think it's important to understand that digital twins really are intended to solve a problem. So the question we may ask is, what problems do structural engineers have that a digital twin can help us solve? And again, this is something that we look forward to hearing your input on. To start the conversation, I'd like to start with an example that might be familiar to some of you. Let's take a look at this image of a multi-story building under construction for a minute. It is a post-tension concrete floor system. It has a central wall core. It's under construction. There's a tower crane in the middle there. And you can see there's a lot of things staged here. This captures really how differently the site can look from what we had assumed to be the case during design. And let's think for a moment what we would do if we got a call from the contractor at this point telling us about an unforeseen problem that arose during construction. What if something got built differently from the contract documents and you were asked to reevaluate your design, but now with different constraints? The question is, what would be the first source of information that you would refer to? How easy would that information be to share? How easy would it be to convey your assumptions to others? And how quickly could you access it? Now, depending on where you are on your digital journey, or for that matter, if you started one, there may be a lot of different answers to this question. You've probably created multiple analysis models that this information would be pulled from, probably some spreadsheets, and the ownership of the models probably varies. In other words, the engineers designing the PT own those models. Perhaps another engineer is responsible for the foundation design, and yet another for the overall load takedowns and stability assessment of the structure. But what we'd really like to have is a single source of truth that will tell us how any change in the design will affect the overall integrity of the structure. So we would propose a digital twin can be this central source of truth and can bring this information together. More specifically, some of the questions that the digital twin can help us answer are, where can I document my engineering decisions so that they are recorded and visible to everyone that needs to see them? Are they handwritten notes just on calculation sheets? Are they a collection of emails? Is there a better way to organize that information? How has the structural design evolved over time? Do I have a clear enough and detailed enough of a history to know why changes were made at different stages along the way? Third, do my structural analysis calculations reflect reality? Are the dimensions, the member properties, the applied loads in my analysis models indicative within an acceptable margin of error of the working master model? And then finally, how do I convey my work to those that I am working with? So with all that being said, what are the ingredients of good technology that would support this process? Well, first of all, I would propose we want a data-rich 3D model that we can easily navigate. We would like to be able to create custom views of the structure, do walkthroughs, toggle on and off different structural systems within the model so that we could, for example, isolate a single floor or a specific framing system and focus our attention just on that part of the structure. Second, we would want the most important analytical results and code compliance checks produced in the desktop software to be accessible within the digital twin, at least the information that will be critical to the decision making before, during, and after construction. Third, a system of exchanging our desktop models with the digital twin so that a history of changes made over the course of the project or even the lifespan of the structure can be maintained. And finally, a means of communicating and coordinating with one another in the context of a 3D model where our decisions can be documented. The platform that Bentley provides that makes this possible is ProjectWise 365. This is really the central point of collaboration where the digital twin exists and all the stakeholders on a project contribute to and interact with it. It is hosted on a web browser, so there's no special software that needs to be installed. to take part in the collaboration or workflows other than the desktop products that you're already using. You just need to be given access to the project by whoever is administering it. There are several facets to ProjectWise 365, but I'd really like to narrow in on the model review and give a feel for how the engineering analysis models that you create are utilized in this environment. So let's take a quick tour of the experience in ProjectWise 365, focusing on the model and design review aspect. This is the ProjectWise 365 site, and we're looking at a structure that we modeled and designed in STAAD, happened to be modeled in STAAD, rail station in this case. It has been converted to an iTwin and includes analytical results, and that's key to the workflow here. I have a few different saved results that I've captured, so I can get to what I want to look at very quickly. These views really can have whatever the portion of the project or structure you're interested in isolated. The analysis software like STAAD or RAM is able to classify the different parts of the structure so that you can easily get to them. So let's do a quick little walkthrough down the boarding platform here, and I'm going to stop here eventually and pan over to this little blue comment icon that is attached to the truss you see there on the left-hand side. This is actually a link to a conversation that I've started that all other team members assigned to this project can see and reply to. And when I select it, I see the conversation thread pop up on the right-hand side there. And you'll also notice that the elements in the structure turn to a range of colors. So these colors represent the utilization ratio of these members as they were designed in STAAD using the steel member design feature. This is the context-specific information that we can query here in the digital twin. There is an analytical specific menu we can access where you can display whatever information the desktop application has handed to it. The controlling design clauses, the controlling load combination, and as I mentioned, the utilization ratios. And again, this will change. The information available here will change based on whatever publishing application you're using. So if you were designing, for instance, a post-tension concrete floor in RAM concept, you'd see results on the PT design available. If I click on an individual member here, I get a little window showing more specific information such as design loads and more specifics on the design parameters. So you can very easily investigate individual members and how they're behaving within the overall model. Now, going back to the question of what we want the digital twin to mean for structural engineering, this is the view into the structure's behavior. And if you think back to that building site that we were looking at, this allows us to more easily answer the question, how much reserve capacity do we have in the system? What parts of the structure would be sensitive to construction changes? How easily can future expansions be accommodated? These are all easily answered and reviewed by anyone in this type of environment. So it really does a lot to democratize, if you will, the engineer's information and makes it far more accessible. There are also simpler ways that we can use the review tools here, in more of a classic design review context. Here, in this screen grab, we're color coding each of the elements in the structure according to their section profile. So what we have here is a very easy way for a reviewer, perhaps a project manager, a principal, a building department reviewer, to validate the assumptions made by the design engineers in the analysis models. And that's another example of what we mean when we say the information is no longer hidden. What otherwise might be tucked away on someone's desktop is now front and center and available for back checking. And note that really any of the quantities in the menu here can be color coded. So just as an example, another useful application of this might be to check the material strength assumptions in a multi-story building construction to ensure that the concrete grade is consistent with what is specified on the drawings. So you might ask, how did we create the digital twin in the first place? Well, it can be created directly from the RAM STAAD or microstrand models that you've created on the desktop. we tie the desktop programs to ProjectWise 365 with a common interface, and you see that in the center of the screen there. This accompanies the desktop software and manages the communication between the analysis model that you're working on and ProjectWise 365, where the digital twin lives. You publish the model simply with a push command, and since the workflow is inherently bidirectional, you can also pull from the digital twin back into the analysis program. So I'll show a simple little sequence here on how the push and revisioning works. And just as an example, suppose that in this STAD model here, we upsize the structural columns down at the bottom in the model. What we would do is we would simply do a save. After we've rerun our analysis, rerun our design checks, we'd simply do a save. We'd press the push button in the little widget that we see on the right-hand side here, and this will update the digital twin. If we'd like, we can review at this point how the new and previous models compare to one another before we actually commit the change. This is an intermittent interface that you can bring up here that you see if you'd like to do differencing on any two states of the model over time. And the color coding tells you what elements have changed, and the details are shown in the pane to the left. And you can be selective in what you want to push to the digital twin. If there are changes you've made in the analysis software that would be superfluous maybe to other disciplines, you can simply reject those specific changes and commit only what's needed for the entire workflow. Once we commit the change, it will be added as a new revision in the change history that you see on the right hand here, which is maintained the whole time during the coordination between the two models. I think it's worth reviewing the change management aspects of this a little bit further. This is a very important and powerful ingredient in this technology. Each time a push is done from a desktop program to the digital twin, it's updated with a revision state. And this is more than just a marker. It's actually a model that we can recover and roll back to anytime we need. I should also emphasize that structural digital twins created in this workflow can easily coexist with design models from other disciplines on ProjectWise 365. Just as an example, this is a high-rise that is placed on the site model, which actually came from MicroStation. So the publishing came from two products in two completely different domains, structural and design model. These types of models can also include reality meshes, like we saw in part of the presentation earlier for better context. So what are the key takeaways of all this? Well, I think the first is that the digital twin, as we see it, can really expose structural engineering data that is more important in decision making that really is otherwise hidden in our day-to-day work. And while this information can be a range of things, we believe one of the most underutilized sources is analytical and design information describing the structure's response under loads and compliance with building code checks. And with a set of applications that are well integrated with the digital twin, we can use this information in more ways that are useful to structural engineers and the stakeholders that they work with. The second takeaway is that the use of the digital twin as a central coordination hub, where discussions, assigned tasks, decisions that would otherwise maybe be lost in email threads can be consolidated in the context of a 3D model for easy visual reference. And the last key takeaway I would offer is the ever important timeline of change that is stored as we make changes to the models, with each point in the timeline being a complete description of the model that we can restore or query at any point. This gives us the ability to interrogate the design at any stage along the course of the project, or even the lifespan of the asset itself. Okay. So this is a brief overview of what we've been working on. The workflows we've demonstrated here will be available in an early access program starting a little bit later this year. And this EAP will be free of charge to participate in. I also want to mention that the product manager overseeing much of what you saw here today, and who is among really the most active and passionate in developing these workflows for our industry, is based in Sydney. His name is Wentao Zhang. He's located in our North Sydney office. In fact, some of you may be speaking with him already about this very technology and already helping shape it. If you are interested in participating in the EAP, feel free to send me an email with the subject EAP and just reference this webinar. And we're happy to work with you to get set up once the software is available a little later in the year. I believe we'll have a question and answer session now, but I just want to say really quickly, I highly encourage you to reach out directly to us, directly to me. We'd love to hear your experiences with the digital twin and where we need to go from here. Thank you everyone for attending today, and I look forward to your questions and comments.
Hi, sorry for that short delay, and thank you to our speakers for this afternoon, Shiraze and Josh. I also want to thank everyone who sent through questions on registration. That's very much appreciated. And for people that are sending through questions in the chat box that we have here. If you do have a question, we've got quite a few minutes, so please, there's still time to send them through. We'll try to get through as many as we can in the next 25 minutes. I might start off with you, Josh. We have a question that's come in. And it's a big good afternoon to Nick, and Nick's in New South Wales, and he's getting straight to the heart of the matter, asking, on average, how much will it cost? Can you please give us a range of cost, minimum to maximum costs? Josh.
All right, thank you for the question. So the short answer to that is I cannot yet, but the good news is that answer should be coming soon. What I can do is talk a little bit about what's included in the service. So what we showed today was ProjectWise 365, which is one of the iTwin solutions that we offer. There's also a iTwin platform that you can develop apps on, and then there's the Bentley out of the box, if you will, off the shelf solutions that are based on iTwin, and that's what ProjectWise 365 is. There is a category of different services inside of it. The ones that we saw today are the more 3D model centric services, and that included the design review services that we demonstrated, and the synchronization, the cloud-based synchronization that we saw. A couple things that we didn't get to today are the file sharing service and the issues resolution service. And so what I can say is that the pricing this offering is going to be a function of which one of those you're interested in. But like I said, hopefully in the coming weeks, we'll have some more to share for you on that.
Thank you for that. We've had a lovely question that has come in from Hilton, and to you, Shazare. And Hilton is based in New South Wales. Good afternoon. He's asking you, what are some parts that you enjoy about your current roles?
Well, that's a very good question. Thank you. So in my position and role today, I've been transitioning from consultant to construction, and there's been a lot of fun, working out in the field. And to be honest, I've never been an out-of-the-box engineer, if you think about it. I have a civil engineering background, but I've always been interested in coding and solving workflows and finding solutions for complicated problems. So what I like about today is that I get to be exposed to different projects across the globe in my position, and each one of them comes with different complexities and different types of solutions for the same problem, and I get to get access to different software development technologies, including some that Josh was mentioning, like the iTwin platform, to be able to develop customized solutions on top of existing solutions. So to be honest, I really love still to code, to be involved in the projects, to sit down with the clients and talk through what are the the different challenges within the project, and come up with ideal and possible solutions, and then maybe being able to implement some of those solutions in one project and be able to scale it in consequence projects.
Thank you for that. You just touched on Bentley's iTwin platform, and Farham in Victoria, Josh, is asking you how mature/capable is Bentley's iTwin platform to be utilised in smart asset management, i.e. monitoring asset performance by developing its digital twin? Thanks, Josh.
Right. Yeah, I think there's some great case studies out there, and I think one of the areas, the specific sectors where there's been the most impressive work done is in the automation of inspections. And I showed a couple of examples on the first slide I showed there, where engineers are taking the context capture software, doing drone captures of an entire asset, and then turning that into a digital reality mesh, and then in many cases superimposing that on or combining that with the design modeling that they've done. So, I think that's really two of our strengths at Bentley: the reality capture and then the design modeling part of it. There are also to go over here in the United States, I recall a case study where the Department of Transportation, the Minnesota Department of Transportation, used a similar workflow to automate inspection of their bridges. And the precision is to a point where they can detect not only whether there are cracks in the concrete in some of these bridges, but how thick they are. They can gauge not just how long they are, but how thick they are. That was one of the things they mentioned that stood out. Obviously, that's kind of on one end of the spectrum of maturity. On the other end, we, as you can hear today, we're kind of in the early goings on what this workflow means for structural engineers, and particularly on the analysis side of things. We have some ideas. Part of the reason of presenting like this and hearing from you and having these conversations is we want to know what's most important to all of you, and really what the next steps we should take are. So we're kind of a little more on the getting started with this, I'd say. So that's kind of the range of different levels of maturity I'd mention.
Thank you. Thanks for that, Josh. Back over to you, Shazare. We had a question from Jawaha, who is also in New South Wales, asking, what do you see as the top 3 challenges needed to enable digital twins? Thank you.
Again, very good question. I think there are 3 major challenges, not just for digital twins, but for the whole digital transformation journey. And for me, are communication, collaborations, and coordination. So to be able to address digital twins today, we really need to get together and find a common platform, a common way of exchanging information. We need to find a common language to exchange information. Most of the times, working in different projects, sometimes you use a platform and authoring tools, use multiple authoring tools, and then on another project, use different authoring tools. But the bottom line is that everyone talks a different language. So the real problem is around abstracting informations in a more structured way, in a more under some kind of governance, to be able then to talk the same language, which is, I think the biggest challenge when it comes to digital twins. So you can literally have in this way multiple authoring tools, multiple companies, multiple stakeholders being able to collaborate at the same time on the same project, talking the same language and talking the same data, and then use those data in a proper way to go back into their authoring tool. So there's few technologies around to be able to abstract information from the models in a more common way. And that's, for me, the kind of goal that the market and the industry need to target to be able then to enable everything about digital twins.
Thank you for that. And Josh, would you support that? Do you have a different view on the top 3 challenges to enable digital twins?
No, I agree with that. I agree. Cesare had some great points there. I think I think one of the challenges is what exactly, and I'm coming a little bit more from the software perspective, I realize, but what is it that you want to get out of it? There's all kinds of things that we could possibly pull from everything that we develop needed during the course of a project, especially when you consider kind of all the stakeholders involved. But I think one of the important things that's really going to make the job easier down the road and have the software be less of an obstacle and more of something that truly helps you along that process is identifying what it actually is you want to get out of it, and what specific things you're trying to get out of that workflow, and how you're working together.
Thanks, Josh. And just sticking with the software, Hilton, good afternoon, Hilton, is in South Australia, is asking both of you, but I think we'll start with you, Josh. How long would it take for an engineer to be competent in the use of the applicable software? And how important is engineering knowledge in confidence in the recommended designs?
Well, I don't know if I can quantify it. I think Cesare might be better in that respect. What I can say is, and hopefully this came across in what I demonstrated, is we're really trying to make the digital twin and what you need to build it and interact with it as much of an extension of what you do right now, present day, as possible. You know, we don't want it to be this new thing where suddenly you're working differently. I think we're all structural engineers are very comfortable and have grown. You know, it takes years to build confidence in a certain software that you use to design and do your analysis checks and your code checks. And the last thing we want to do is kind of pull the rug out from under that. So we've worked pretty hard to kind of build the experience around what you already do in your desktop applications, and then just make the publishing, the interoperability, those steps that are required to build the digital twin, just as an extension of that. And so I think, my own personal experience, as much of a consumer of Bentley technology as anybody else is, it's pretty simple. You know, the basic navigation, getting familiar with the 3D model, how to navigate, how to get to certain views quickly. That's all pretty intuitive and should come pretty easily. The other part of the question about engineering judgment, I believe it was, I cannot emphasize enough that there is no replacement for it. No matter what we build, no matter how sophisticated the software gets, there's never going to be any replacement for the engineering knowledge and engineering judgment. That is something that's always going to remain. There's no replacement for that.
Thanks. Cesare, do you want to comment on that further?
No, totally agree with Josh. So for me, number one, of course, engineering knowledge. So it's important that when you use a software, you use a software with the right mindset, with the right ideas, with the right design knowledge. So you can design a retaining structures. And then you can design a crap retaining structure just because you don't know exactly how the retaining structure should work or how the retaining structure should be built. And so the engineering knowledge is a key component. What I would say is let's not concentrate on the tools because the tools are commodities. You know, today you use one tool and tomorrow you're going to use another tool. You're going to be able to use another tool. What I think everyone needs to concentrate is probably a change of mindset and a change of skill set as well. So when it comes to the new skill set you're going to be able to master, is definitely not knowing a piece of software, is knowing and changing the mindset and try to think about out of the box. I usually say that today, when I think about bringing someone to the team, yes, we can bring engineers into the team, and we do that because we are an engineering company. But I also think about bringing in my team a data scientist, a physician, or someone that has been working with game development. And the reason for that is that I don't want an engineer to think like an engineer. I want someone to be able to think about how to solve a a common problem of the industry from a completely different perspective. And I think that's the kind of mindset everyone needs to shift to be able to engage with the new technologies, including digital twin.
Thank you for that. And that's a great response. We've had a question, Josh, that's come in from Gerard, who's in New South Wales, asking, does Bentley provide software to assess carbon footprints of single-storey residential and industrial construction, and in particular with Revit compatibility? Thanks, Josh.
Thank you. Apologies for that, everyone. We have a building information modeling product called Open Buildings. And within that, there is a energy simulation feature that includes things like the thermal aspects, lighting, and some other energy optimization features in there. And so that's what I would say is the closest thing we offer. In terms of the Revit compatibility, we do have that through a couple of different means, through a couple different frameworks, depending on whether you're dealing with one of our DGN based, kind of built off of MicroStation, one of those applications, or whether you're dealing with our structural analysis software, which has its own, like we saw today, has its own interoperability framework that connects it to most BIM applications and other structural analysis softwares.
Thank you. Might just go across to Queensland here. We've had a great question coming in from Helen, and we'll start with you, Josh, but she has directed the question to both of you, asking, what is the scope for including artificial intelligence in the use of digital twins from conception to managing the infrastructure? Josh.
I'm tempted to ask Cesare to start, because I know he talked a little bit about that
Sure.
in his presentation. But yeah, Cesare, did you want to go ahead?
Yeah, sure. It's again, I probably briefly touched on that also in the previous answer. Today, it's all about changing this mindset, changing these skill sets, and artificial intelligence for me is after digital twins and computational design, it's probably the third buzzword. I can think about probably 10 buzzwords in the late days, but the main idea is it's all about predictions. So if you have structured data coming through your models throughout your design process, and those data are structured enough to be able to run some kind of machine learning algorithm on top of it, you can get a better prediction. I briefly touched on generative design previously, in terms of optimizing the trajectory of a tunnel. Well, that's not possible if you don't use structured data, for example. And the more you collect those data, the more you're going to be able to predict a better trajectory in the future. So for me, it's all about predictions of future and learning from the past, basically.
Thank you. Thanks very much. And maybe staying with you, that we've had a question that's come in from Prathapa asking, which Python libraries would you use to read and edit IFC files?
Yeah, that's a very good question. So Python is one of the programming language that is at the top of the charts in the last, I think, probably 1 or 2 years. So it's very popular. There's one very common library that has been used for IFC, and it's called IFC Open Shell. It's an open source library. It's built on top of C++, so it's very fast. It's very quick in terms of traversing large files. But there's also other libraries. If you want to open up your mind again to different, I would say, programming languages and software platforms, there's also a very new library called IFC.js, which runs on the web. And the web looks like being the future for all these platforms. And Josh can extend on it, but iTwin platform, it's all based on JavaScript. It's all based on web services. So is literally, I think, not the future. It's just the present now, looking into web APIs and those type of things. So yes, Python OFC open shares, but also open your mindset to learn other programming languages for the web, like JavaScript, and then you can tap into other libraries like IFC, JS. But they're very similar. Once you learn one, it's all the same.
Josh, do you want to expand on that?
So Amanda, I might actually expand on the AI question, going back a question.
Yeah, sure.
I wanted to mention just some kind of steps we've taken into that realm of computation. And I don't know if everybody here, or those that are purists, might not consider this artificial intelligence, but for our one of our software applications that designs reinforced and post-tension concrete slabs, which is called RAM Concept. A couple of years back, we implemented a new way of optimizing the tendon layout that no longer requires the user to identify, to completely describe the tendons before they check the design. In other words, you basically input a basic plan description of the tendon, and the software goes about optimizing the high and the low points of the tendons in the slab, selecting the quantities of the tendons. And this was all done using by plugging RAM Concept into a genetic optimization algorithm, and it's hosted on the cloud. It does come through the digital twin in the sense that tendons can be exchanged from concept into the iTwin format. And so I wanted to at least explain that a little bit and talk about some of the small steps that we've taken in the AI category.
Thanks for that. Thank you for that. I mean, it's interesting that there's quite a lot of questions coming through around skills and capability, and if we sort of put that into that context of the shortage of skilled engineers in Australia. Chris is asking a question to you, Shazare, saying, how would someone with structural engineering background but limited previous BIM experience transition into a BIM engineer? Is it just by learning more software, or is there a course you have to study? Are you able to answer that for us?
Yeah, of course. So again, all of these are very good questions, and I can sense, the type of questions coming from a bit of concern. Do I know enough to be called a BIM engineer? Well, the answer is that, to be honest, I'm not even thinking more about the word BIM. And again, it's all about not really learning new softwares. It's more about learning new ways of using those softwares. So we can always find someone that is an expert, is an expert in using that specific software. But how about we bring this person and we move this person into another software? Suddenly, this person doesn't know what to do. But how about we have someone that knows exactly how to solve that problem, and then can articulate the solution to the problem? And that's what we are looking for in the future. Because with all this machine learning, all this AI coming through, and Josh just made a fantastic example of the tendons. I know what a tendon is. I know how to design a tendon. Let the computer to do the heavy lift of the job, and then me as an engineer understand if the solution is right or wrong. So that's the type of job we need to do in the future, not just pushing buttons. So to answer the question, and hopefully I answer the question, I don't think you need to study any new software. Definitely knowing a little bit more about computational design, about data science, about machine learning, even just scratching the surface will let you move forward in the future, because all the types of technologies that are coming are not meant to force you to push buttons, but other forcing you to read results and set the rules to get those results. So for me, anything that goes around data science, anything that goes around computational design or generative design. And it doesn't matter if you are a structural engineer, you are an architect, or you are a civil engineer. We're all going towards the same goal. So anything that goes around this will definitely let you be prepared for what's coming.
Thanks for that. And thank you. You're absolutely right. We're having a lot of questions that you do get a sense that there is some nerves around how much you need to know. And Josh, we have talked about this, but Hilton has just asked, can Bentley software be used to design most types of civil and structural and infrastructure? And then again, Hilton's saying how many months to become proficient, but maybe if we could talk about, can your software be used to design most types of civil and structural infrastructure? Thanks, Josh.
Sure. Yeah, we have a number of different applications that specialize in certain sectors. We building off of MicroStation, we have Open Buildings, which is our BIM software, Open Roads, Open Plant. And really, I would say what's nice about these is that they are all built from essentially the same platform. If you know one of them, if you know the interface of one of them, you know the interface for all of them. So that's kind of the pure design modeling, 3D modeling aspect of it. And then you get into the analysis products like the geotechnical analysis, the Plaxis, structural analysis, which I look after, which is STAD and RAM, MicroStrand, and together, considering the interoperability between them and just the breadth of the solution that they offer, I think we have most assets covered, and it's a pretty solid overall solution.
Thank you for that. And just staying with you, Josh, because we've had an interesting question coming from Ali. Good afternoon, asking, we use scripts a lot in FEA. How do you link scripts in the FEA to the overall digital plan? What software do you use as the best? Thank you, Ali.
So scripting, and actually I'm going to go back to RAM Concept, the product I mentioned a few minutes ago. We fairly recently introduced a system of Python scripting that you can do in RAM Concept recently also. And so what you used to only be able to do using the user interface, you can now write scripts for and automate essentially the creation of a model. I think we're to the point now where we're automating the output of some of the information into tables. So that's one example that's kind of built directly into the software. Going a little more free form, most of our products have programming interfaces that you can plug into. Certainly the design modeling products do. The most of our kind of core structural analysis products do. So STAD Pro, RAM Structural System have a programmer's interface that you can use to kind of fill in whatever gaps you have in your workflow now, and to the extent possible, you could include scripting in that as well.
Thank you for that, Josh. Shazara, we've had a great question come in from Hilton asking, wouldn't standardized structural components be less expensive to manufacture rather than many different components with different geometries? Thank you.
Yeah, that's definitely the truth, and this is all related to what we call design for manufacturing types of design, which is pretty popular in the precast and the healthcare types of projects. Is not that common in, for example, in infrastructures where most of the times we have very bespoke types of structures. But what we're trying to achieve now is again, using algorithms to come up with solutions to minimize the diversion of types of structures. If I can give you an example of a girder types of bridge, you can usually, if the bridge is very complex, is on a curve, is on a skew, and those types of complexities, you end up to have different girders. A huge amount of number of types of girders. what we try to do is to use computational design and generative design to be able to reduce as much as possible the types of girders, so we can manufacture just the right amount of girders to support that type of project. And this is more an optimization types of problem that can be solved using computational and generative design. But that can be applicable to any type of structural analysis problem, like facade optimization, or if you go back to the bridge example, the precast barrier, you really don't want to have a barrier that is with a length of 4.25 meters and the next one being 4.27 meters. So you just want to make sure that you kind of place your precast barriers in a way that you minimize as much as possible the number of types. So definitely, yes, the future is going to be optimizations of structures to reduce the number of bespoke structures, and this will definitely reduce costs because we can manufacture objects outside, and then we can just ship the objects or deliver the objects to site, and with the right tagging systems, the right information embedded in the digital twin, we should be able to immediately put that object into place on site with the right information.
Thank you for that. And as always, we're rapidly running out of time, so I might make this the last question, which is coming from Noel. To you, Josh, asking, is digital twinning in high-rise building constructions can also be intertwined with mechanical, electrical and plumbing design systems, MEPs? Josh?
Yeah, so that's the multidisciplinary aspect of it is certainly critical, and one that we're looking to support. I showed a little screen capture there of a structural skeleton sitting on a site that was modeled in I believe it was MicroStation, and had some adjacent buildings, just outlines of adjacent buildings there. And we could have easily included those other disciplines along with that model also. Going back to the open buildings, or just your general, a generic BIM platform, those come through to the iTwin through a specific bridge. That's how they get published to the iTwin from the desktop application, is just the bridge that they publish to. Once it's into the iTwin, it's all the same, right? It's all the same platform, all the same underlying information, and it can be coordinated against. You have it all there in the same view. So yeah, we certainly recognize that, and what you saw coming from the structural analysis software in the demonstrations can easily be integrated with the other disciplines.
Thank you for that. And I am sorry, but we have run out of time this afternoon. Please join me again in thanking Shazare Keduru and Josh Taylor for taking their time and sharing some wonderful insights in today's session. I'd also like to take the opportunity to thank Engineers Australia's industry partner, Bentley Systems, for making this afternoon's webinar possible. As always, we'd appreciate your feedback on the program, and also to help us improve and plan future sessions. If you could please complete a short feedback form, which is linked in the description box below. Thank you again for joining us, and I look forward to seeing you at our next Thought Leaders webinar. Good afternoon.